Hi, in this video, we are going to see the proof for some of the limit properties. So here's the first one. Limit x tends to a, x raised to n, a raised to n. This gives us n, a raised to n minus 1. So we are going to see the proof of this. This is a. So when we say x approaches a, so x is here, it is closer to a. So this is a plus h, this is a minus h. So as h approaches 0, we can say that x approaches a. So let us write this. Limit x approaches a can be written as h tends to 0, a plus h raised to n, a raised to n. And here we have a plus h minus a. So we get limit h tends to 0. And over here we get the expansion, binomial expansion, nc1, a raised to n minus 1, h, nc2, a raised to n minus 2, h squared, so on, till we'll get h raised to n. And here you have a raised to n, the whole upon h. So these two terms will get cancelled. We have limit h tends to 0. Now in this term, I can take h out. I'll get nc1, a raised to n minus 1. Here I get h, and here I'll get h raised to n minus 1, the whole over h. Now we know that h tends to 0, h is not equal to 0, so this can be cancelled. So taking the limit, we will have n a raised to n minus 1. All the terms following will become 0. We get the proof. Limit x tends to a, x raised to n minus a raised to n upon x minus a will give you n a raised to n minus 1. Now there is another part to the same property. I'll show you that. Limit x tends to a, x raised to m, a raised to n upon x raised to n, a raised to n. So in this, if we divide x by a, and you have x raised to n, a raised to n, x minus a. How can we divide it? We know that as x tends to a, x is not equal to a. Therefore, x minus a is not equal to 0. Because it is not equal to 0, we can divide it. And then we apply the property. Here you get m, a raised to m minus 1. And this will give you n, a raised to n minus 1. So we get m upon n, a raised to m minus 1 minus. So this gives us m upon n, a raised to m minus 1. We have limit x tends to a, x raised to n minus a raised to n. This is n, a raised to n minus 1. X tends to a, x raised to m. M upon n, a raised to m minus n. Now moving to the next property. So the property is limit x tends to 0, sin x over x is 1. So we are going to see the proof for this. So we go back to the unit circle. So this makes an angle theta. I will drop another perpendicular over here. Let us name this as O, A, B, C, and D. Area triangle OAD. It is less than area sector OBD. It is less than area triangle OBC. So this is visually also very easy to observe that when you're talking about area of the triangle, you're talking about this. When you're talking about the area of the sector. So that includes a little bit of this portion here along with the triangle. And then when you're talking about the bigger triangle, then we have a little excess portion that is this portion. Okay, so that's the reason why these areas are not in the order that they are. Okay. Now, how to find the area of the triangle? So you know that this drop is a 90 degree. This is a tangent. So this is half base into height. Area of a sector is half r squared theta. So I'm writing this as OB squared into theta. And area of the triangle is half into OB into BC, right? The first thing we can see that half can be striked off. And then over here, what we have is OA. Now, we know that for a unit circle, okay, if I draw another one here just to explain, if this is theta, this point, which is x comma 1, it is cos theta sine theta because the radius is 1 over here. So when we have OA, here you have OA as cos of theta and BA as sine of theta. So OA will be termed as cos theta into sine theta. And then we have OB squared. Now OB is equal to 1 because this is a unit circle. So that is left with just theta. And then you have OB again, that's 1. But BC. Now BC is termed as tan of theta. So in triangle OBC, if you take tan theta, which is opposite upon adjacent, so this is equal to 1. So therefore CB is nothing but tan theta. So let me write that over here. This is tan theta. Now we divide by sine everywhere. So you get cos theta less than theta over sine theta. And this is tan theta upon sine theta. Okay. And if we reciprocal this, the inequalities change their sign. So we have 1 upon cos theta. And this is sine theta upon theta. And this tan upon sine gives us 1 upon cos. So when we reciprocal this, we just get cos. Okay. The next step in this is taking a limit. So over here, I'm writing this as limit theta tends to 0. This is 1 upon cos. This is sine theta over theta. And this is limit tends to 0. This is cos theta. Now in this, we are going to use the sandwich theorem, or what is also known as the squeeze theorem. So if we think of functions which are given by this, okay, so here we have a function f of x, here we have a function g of x, and this is another function, say p of x. And we are talking about a point on the x-axis, which is say x equal to a. So from the graph, we can see that f of x is greater than p of x is greater than g of x. And when we talk about a particular region over here, in that region also you can see that the function f of x is greater than p of x and then g of x. So this can be written like this: limit x tends to a f of x, limit x tends to a p of x, and limit x tends to a g of x. So what the theorem says that for x equal to a or near x equal to a, if f of x and g of x take a specific value, that means the function p of x should also take the same value. So what does this imply? Limit x tends to a, p of x is also equal to L. So we are going to apply this over here. So as x approaches 0 or theta approaches 0, we know that cos of theta will be equal to 1. So therefore, this limit and this limit will be 1. So we have 1 greater than equal to limit of theta tends to 0, sine theta over theta, and this is also 1. So therefore, by applying the squeeze theorem or the sandwich theorem, we get limit theta tends to 0 sine theta upon theta as 1. Okay, so writing the result here again, limit x tends to 0, sine x over x is 1. Now using the same property, we can say that limit x tends to 0, tan x over x is also 1, because this can be written as sine x over x into 1 upon cos of x, which will be 1 into 1, that is 1. Let's move to the next problem.